Hi everyone, welcome back to our series on numerical methods. And today we're talking about convergence of sequences and series in a series of delicious events. So, an engineering student walks up to the deli counter and asks for a wheel of cheese. The second asks for half a wheel, the third for a quarter of a wheel. The deli worker plonks 2 wheels of cheese on the counter and says, "Sort it out amongst yourselves." So, how does the deli worker know how much cheese to put out, and how much cheese should students infinitely far down the queue expect to get? We're talking about convergence. So convergence is to tend toward some finite limit L and keep getting closer to it. As n moves to infinity, as we get further and further down the queue. If something doesn't converge, we say that it diverges or is divergent. So you'll be familiar with some functions that do this already. So if we think about the function 1 over n, that goes down and approaches 0 as n goes to infinity. Or if we have an oscillation whose amplitude decays over time, that also converges. Functions like exponents blow up, and y equals x keep increasing. So they're divergent. But we can also think about things like oscillations with constant amplitude, which don't blow up, but they don't converge, so we say that they're also divergent. So convergence is a property of infinite sequences and infinite series. Infinite because if it's a finite series or a finite sequence, we could just calculate the answer. So a recap on our intro to sequences and series. A sequence is just a list of values. A series is a sum of values. And we've written here n equals 0, but n can start at any point. Okay, so let's talk first about the convergence of a sequence. So our question is, how much cheese should students infinitely far down the queue expect to get? So let's start with the definition. So a sequence an converges to a limit L if for all epsilon greater than 0, there exists an n such that absolute difference between an and L, the limit, is smaller than epsilon as n gets larger and larger. So what we're talking about, if we have some sequence that looks like this, is an envelope whose width is epsilon, and we say that we stay within this envelope as n goes to infinity. For today, we're going to talk about finding the limit of a sequence by inspection. So we're going to recognize sequences whose behavior we already know, like the functions that we showed earlier, and take the limit as n moves to infinity. So the students have formed the sequence 1, half, quarter, eighth, and so on. So the sequence is 1 over 2 to the n. So to find whether or not it converges and what it converges to, we take the limit as n moves to infinity of 1 over 2n. So we've got 1 over 2 to the infinity, which is 1 over more infinity, which goes to 0. So the sequence converges to 0. So students at the infinitive point in the queue don't get any cheese, but it is what they asked for. So we know how to deal with sequences. What about the convergence of a series? How does the deli worker know how much cheese to put out? So this is the sum of all cheese used up by the students. So we're going to take a step back and go through the queue one student at a time. So we have the sequence of students, how much each student is asking for, the total amount of cheese given out, and the total amount of cheese given out graphed as we go through the queue. So student 1 is asking for A1 amount of cheese. They're asking for 1 wheel. So we've given out 1 wheel of cheese, and the total amount given out is A0 for a sum of S0. So that's the total amount given out so far. Student 2 asks for A1 amount of cheese, just half a wheel. So we've given out 1.5 wheels. The total amount of cheese given out is A0 plus A1 for a total of S1 amount of cheese given out. Student 3 asks for A2 amount of cheese, quarter of a wheel. So we've given out a quarter of the wheel. And in total, we've given out A0 plus A1 plus A2 for a sum total of S2 amount of cheese. So what you may have noticed is by drawing this cumulative amount of cheese, we're actually forming a sequence. And this is the sequence of partial sums. So we can write that the kth partial sum, sk, is a0 plus a1 plus a2 and so on to ak. And we have a sequence sk as k moves to infinity, as we move down this infinite line, of s0, s1, s2, and so on. And because we have a sequence, we know how to see whether or not this is convergent and what it's convergent to. We call that value s. So we say that if the sequence of partial sums converges to some limit s, the series converges and it sums to s. So to summarize that, we have an infinite series, sum of an, which can be split into partial sums, like so. We have an expression for the kth partial sum, sk, and because we have a sequence, we can find the limit lim k goes to infinity, and if it converges to a value s, then we say that it sums to s. So here is that all condensed down for you, and we say that if the sequence of partial sums doesn't converge, then the series is divergent. So our algorithm is that we find the partial sum sk, we find a formula for sk if we can, and we take the limit of sk as k moves to infinity. So in our example, we have the sum of 1 over 2 to the n. So feel free to stop here and have a go at it yourself. A hint, this is a geometric series. Come back to us once you've had a go. Okay, let's carry on. So the first thing is to recognize that this is actually the geometric series r to the k. And that means that we have an expression for this series. So we have the sk is 1 minus r to the n plus 1 over 1 minus r, where r is half. So let's pop that in. We have sk is 1 minus half to the k plus 1 over half. So we have 2, 1 minus half to the k plus 1, which is just 2 minus 2 times half to the k plus 1. So we want to find the limit as k moves to infinity, the limit of the sequence of partial sums. So we have 2 minus 2 times half to the k plus 1. And because half is less than 1, as k goes to infinity, this whole term equals to 0. So the sequence of partial sums converges to 2, which means that the series is convergent and that it converges to 2. So the Deli worker really knows their series, which is just as well given the very strange requests of these engineering students. So what have we learnt? We've developed some intuition for convergence, that it's to tend towards some finite limit L and to keep getting closer to it. And if something doesn't converge, it diverges. And we have a nice definition for that. That we can find the limits of a sequence by inspection, sometimes, by recognizing sequences whose behavior we already know and taking the limit as n moves to infinity. And then for the convergence of series, we know that we can express a series as a sequence of partial sums, and that we can take the limit of that sequence, and if it converges, so too does the series, and the limit to which it converges is the limit of the series. We also know that if the sequence of partial sums diverges, so too does the series. Okay, so here's a nice condensed sheet of the algorithms and the definitions that we learned today. And a new queue has formed, and they have even more strange requests in the form of some exercises for you. So do have a crack at these. Let me know if you have any issues. Next time we'll be looking at the properties of limits and criteria for convergence and divergence in much more detail. So we've got some resources, so these have some examples that you can work through, as well as some real-world applications of infinite series and convergence, and a fun cartoon on the real-world consequences of misusing the convergence of series. Okay, thank you for coming, and I'll see you next time.